the low-pass filter network with an amplifying stage. Hello everyone, my name is Rafael, I am an electrical engineer, and in this video I'd like to invite you to see with me a filtering network of the low-pass kind with an amplifying stage. And to do so, I chose this circuit here. Our objective is to cut high frequencies over 1 kHz and see that we wish to amplify the input signal. We are receiving a signal here and we want to amplify it and select the frequencies. We don't wish to amplify high frequency harmonics. We want only to let pass low frequencies. See that we are using an amplifier. We don't want to have any kind of gain. We want to have a specific gain that's going to suit us, and to do so we are using a feedback loop around this operational amplifier with R2 and R1. In this way we can control the gain. And here we are using a capacitor and a resistor to implement a filtering network of the low pass kind. See that the gain from this point here, this terminal here to this terminal here, the gain of the operational amplifier in the inverting configuration is going to be equal to Vk divided by Vs. And see how it is the inverting configuration, the input signal is entering through the inverting terminal of this operational amplifier. Then the gain is going to be equal to the negative of the division between R2 and R1. Okay? And we wish to establish that the gain is going to be equal to 100 volts per volt. We're not going to worry about this negative sign here because we can get rid of it easily. And this is the gain that we are going to work with. And now let's take a look at the filtering part of this network. Okay? The transfer function of the filtering part of this network is going to be equal to 1 plus SRC. Okay? This is the transfer function of this filtering network here. We substitute this by this. Okay? We substitute the capacitor by its reactance, and the resistor is represented by its resistance. Okay? When we calculate the transfer function, we find this. Okay? Here it is R3. Okay? And when we bundle these things up, we get that V0 divided by Vs is equal to negative R2 divided by R1 and 1 plus SR3C. Okay? And here we are going to call it the gain. K is equal to minus R2 divided by R1. We're going to call it the gain and K above in the numerator and 1 plus SR3C in the denominator. This is going to be the transfer function that we are going to operate with. But pay attention that S is equal to sigma plus JW. If there is no attenuation of the input signal, we can say that S is equal to JW because sigma is going to be 0. Sigma is not 0 only when there is attenuation of the input signal, but if the input signal is not attenuated, then sigma is 0. Okay, we're going to use this here, remember, for later. Alright? Then we can go to a store, we can go to a warehouse, and then we're going to buy these components here. They are extremely cheap. And we're going to select what we want. Okay? We want to have a gain of 100. And we want to have a transfer function just the way we wrote on the board here. So let's save these results here. we want the gain K to be negative 100, and this is going to be equal to R2 divided by R1. R2 is going to be equal to 100 kilo ohms. We are going to choose freely, we can freely choose any value. It is easier to operate with 100 kilo ohms, and R1 we are going to choose to be 1 kilo ohms, and if we divide this by this, we get this, okay? So this is what we are going to operate with. And now let's take a look at the resistor R3 and the capacitor of the circuit. We're going to have to understand that tau equal to R3 times C is the time constant of the filtering stage of this network. Okay? And the inverse this frequency here is the inverse of the time constant, and this is equal to the inverse of R3 times C. Okay? What we wish is to cut frequencies above 1 kilohertz. We're going to see here that we are not going to be specific about this. We are going to be around 1 kilohertz, and we are going to find a frequency that is not 1 kilohertz but is close to this. And we are going to freely select the values of the resistor and the capacitor, and R3 we are going to choose to be 2 kilo ohms, and the capacitor is going to be 100 nanofarad. Alright, if we put these values here, we are going to discover this. Okay, so we are going to find the frequency to be 1 over 2 pi RC, and the frequency that we are going to find is 796 Hertz. So this is the frequency that we are going to operate with. Okay, we wished to make it simple, then we selected this resistor and this capacitor. It is not 1 kilohertz, it is 796, okay? It's going to suit us if we operate with frequencies of 60 Hertz, of 100 Hertz, 120, 200 Hertz. Then we can freely choose this and this to have this knee frequency here, okay? The knee of the curve, the point where the curve starts to bend at 796 Hertz, okay? Then this is what we chose, and we are going to find that this frequency here is 2 pi f, which is approximately equal to 5000 Hertz. So this is the frequency that we are working with, 5000 Hertz. Okay? Hertz, no, sorry, radians per second. Radians per second. Yes, very good, my friends. Radians per second. This is in Hertz. We multiply by 2 times pi, and then we get radians per second. Very good. This is what we're working with. Okay, my friends? Now we are going to have to understand a little bit more of the transfer function. Okay, the transfer function is what we are going to have to understand to see if this is indeed a low-pass filter. If not, we are going to have to change it. We discovered that the transfer function was of the kind k divided by 1 plus SR3C, okay? This was the transfer function that we discovered in the beginning. And then if we say that S is equal to JW, then our T of JW is going to be equal to K1 plus JW over W0, okay? Because we know that T is going to be equal to this, okay? The time constant of the circuit is the inverse of this frequency here. And how do we know? You ask me, how do we know that this is going to cut high frequencies? You see that if we have here a very big frequency, let's say 1 megahertz. 1 megahertz here, I'm gonna have a big number here. I'm going to have a big number here and a low number here, and then this is going to tend to be 0, okay? If we have a very big frequency here in the denominator, a very big number, 1 gigahertz, for example, this going to infinity, then we are going to have a very big number here, and this number here that we selected to be 100 divided by 1,000,000, for example, or 1 billion, is going to tend to be 0, and then we can prove that this is indeed a low pass filter. Okay, my friends? So this is the video that I wanted to make. I hope you guys enjoyed it. I am a teacher. If you want to book a lesson with me, contact me using my WhatsApp number. Guys, goodbye!